In the Washington, D.C. branch, many of you are from outside of Washington, D.C., which we're delighted to have you. But we've been doing for years is putting together a series of events where people can have informal conversations about important technical issues and important advances in technology around the world. And so, of course, we're transitioning that, like everyone is, to more virtual events and taking advantage of the fact that we can reach more people. And so we're glad you're here to work with us today, and we're going to have a very interactive and informal session. There will, of course, be questions available to the panelists. Please just look in the lower right-hand corner by where you have the chat and the three dots. There also is a possibility to call up a Q&A box there, and we'll be keeping an eye on that as time goes by. All right, so let's get to the subject of what we're talking about. As we said in our promotional brochure that got you here, is that this is an interesting time because right now, billions, literally billions of dollars are being invested in the development of a new generation of civil aircraft. Advanced aerial mobility, UAS, you name what you want. It all involves new types of software, AI, machine learning gets tied into much of it, and it's all going to eventually transform the entire transportation system as we know it. It's a very high stakes deal. And so here we have a situation where all of the business cases that people have been betting on require eventually a high degree of autonomy, even completely pilotless. And we all have to maintain a high level of safety because just like in the opening days of aviation in the 1940s, where if someone has an accident, everyone has that accident because we're launching a new type of aviation that people are going to have to gain confidence in. And so we have to then talk about what do we do about this old practices that we've had for years as far as certification, software safety, and so on, and compare that to what we need to do in this new world. So how do we take advantage of AI and machine learning on a proper scale while not compromising safety along the way and while gaining the respect and confidence of the public that has to use it? And so that's what we're here about today. It's and I will tell you that we've had the advantage of being able to see who's registered, and frankly, we're quite impressed. We're glad to have you. We have quite a few experts on board. And of course, mixed among all those experts too are some people going, wow, this is a new thing to me. So we'll try to level set everybody as we go through this. So as you probably heard the chatter back and forth there, we're just, as always in these things, we're trying to get one panelist to come on. There's always some point in the world where somebody's got a bandwidth problem. But I'll start the introductions and he'll join us in a few minutes. And so for the panelists, we have Auntie Christie, who is a British technology inventor and a founder of his company dealing with advanced simulation, AI, and machine learning. He's been operating independently since 2004 and working on technologies that are now embedded state-of-the-art software applications for safety critical tasks in a number of blue chip organizations in the UK government. Previous to that, he was a technology advisor to a global aerospace OEM and introduced into service the fast jet simulation facility that's quite revered by the UK Ministry of Defence as one of the most advanced in the world. And initially, Monty served as in the Royal Air Force as a fast jet pilot, training group, staff officer, and commander of what that time was the largest fast jet training squadron in the RAF. And so he'll be joining us shortly by voice. Also with us today, we have Wes Ryan from the FAA. He is the unmanned and pilotless aircraft let me try that again. He's the unmanned and pilotless aircraft technology lead. That basically means that he's looking at the strategic initiatives in the FAA to facilitate the development of safety enhancement technology applicable to the GA fleet, urban mobility aircraft, and unmanned aircraft. Wes has spent 20 years in the FAA, mostly focused on advanced technology and pilotless technology. He's also done 6 years as a flight test engineer in industry and 5 years working at NASA on flight control and flight dynamics. And we also have Alex, and now that Alex Georges, who is the Innovation Services Principal for the UK Civil Aviation Authority. He's providing technical expertise in these leading programs in artificial intelligence, autonomous systems, and beyond visual line of sight drone operations. He has a background in aerial robotics, a PhD in aerospace systems engineering, and he's highly skilled in such areas as beyond visual line of sight drone operations, autonomous systems, optimization, engineering design, data analytics, and so on. And so that's who we have here today to work through all this. We have a very technical panel with a very non-technical moderator, but maybe I'm here to sort of do some of the translating. All right. So with that, let's start the conversation. Now, first, before we get too far, let's get clear on what AI ML really is, as we're talking about in this discussion on airborne systems. It's surprisingly hard lately to try to get all these terms right, because, you know, if you bump into anybody before COVID that was in this field, they would tell you how they're going to do an agile development project on an AI deep learning system that's going to live on a zero trust network and be encrypted with blockchain. And you'd say, oh, that's great. What does all that really mean? And so I think we need to have the conversation about what do we really mean as we sit here together and talk about this hard nut to crack, which is AI ML in airborne systems. How do we define that? What in this context? And that, I'll tell you what, Monty, I believe you just joined us. If you could unmute, do you hear me okay? Let's give Monty a minute. Hey, Wes, what's your view on what we just said? How do you define all this?
You know, it's a great question. It's an important question to start with today, because there are a lot of different ideas of what artificial intelligence and machine learning mean, depending on the industry, depending on the application. There's a lot of different things that people call AI or ML that, you know, maybe aren't from the technical standpoint. You know, that we have people looking at data analytics, machine learning, you know, this idea of predictive analytics, all these things that are applied to other industries. For the aerospace industry, what it means to me is a system that has a very defined intended function, and that intended function is doing something that makes the team between the human machine, you know, the human machine interface, the pilot and the machine, it makes them better. And those functions are things that a pilot may not be able to do on their own, or do them as well as the machine can. So, you know, instead of just, you know, diving into something that automatically means it's a adaptive learning algorithm, you know, we may have just smart, complex systems that help the pilot do their job better. So, you know, we're trying to put the context of a definition of AI and machine learning into the context of an intended function that is, you know, applicable to something that the aircraft needs to do. And so that's kind of where we start. Yeah, and if it is adaptive and it, you know, has some machine learning aspects to it, then we very clearly define what those parts are, so that the system can be safely used. And so, you know, this idea of what it is and what it isn't, you know, there are certain people who say that unless it has these characteristics, it can't be called AI or machine learning. You know, so we try to define it in terms of the intended function that's being used on the aircraft to start with. Hopefully that helps.
Hey, there's a start. And Monty, I see you, I see your smiling face, and it looks like things have settled down. Are you ready to dive in?
Ready to dive in. Thanks, Bill, and apologies for the delay. We've fought with the technology, and we've got ourselves to a standby camera, so it's better than nothing. And hopefully, you can see and hear me. That may be a good or a bad thing, but at least we should be communicating now.
You're looking quite handsome, my friend. No problem.
You're too kind.
All right. So we were talking about the question of how do you really define in this context AI/ML? How do you think of it when we're talking about AI/ML and airborne systems?
Bill, would you like me to answer that, or come up with my thoughts?
Please do. Please go right ahead.
Perfect. Thank you. AI is a broad area, and it's broader than most people possibly realize. It's been around a long time. It's gone through lots of generations and iterations of how it's dealt with, how it's handled. But there's generally a perception that from a large part of the population that AI will take over the world, and we're all going to end up being a victim of its success and be second-rate citizens compared to these machines that are going to run the world. My own view from where I come from is we're a long way off that. And I think there's a very good article that's out today in the Financial Times. If anyone gets the chance to read it, I fully recommend it. It's about the company, I hope they won't mind me saying, called OpenAI, who have got a new technology that's been launched. And it does things in machine learning and data workings that are far, far superior to a lot of that has happened so far. But underneath it, it doesn't have human understanding. It can't answer simple questions which need human intuition and human intelligence to be able to answer, such as, and this is an example I quote from the Financial Times, if the machine is asked how many eyes are in a foot, it will come up with 2. Clearly ridiculous, but that's the level of understanding that these things have. Very, very limited. So where I think we need to be looking at with AI and machine learning for the future, for the near future, maybe into the far future, is where we have a system that would benefit from machine intervention, from machine help, where the human operator can benefit from having that machine to help him, to keep him out of trouble, to warn him when there's trouble brewing. That's where we can take benefits from AI and machine learning. But we've got to have good data, we've got to have transparent procedures, we've got to have good software architecture, we have to have traceability, lack of bias. A lot of things have to fall into place to allow that to happen. And not least, which is, I guess, one of the reasons we're having these discussions today, is the regulators need to get their hands on it and be really, really comfortable that they know inside out why these decisions are being made by the AI itself.
There you go. Okay. Well, so I think we just added to the piece of the puzzle, reinforcing the notion that, yeah, this is about a particular function, and this is not about generalized intelligence. This is very narrow. And so with that lead in, Alex, would you like to jump and talk about your views in this area?
Yeah, absolutely. And I might sound a bit repetitive now and basically repeating what Wes and Monty has already said, but it's a very important thing that we need to do. And to start with, when we talk about AI, it's not what is considered AI in terms of methods. We're not going to sit here and discuss whether optimization is considered AI or knowledge engineering is considered AI and so on. I don't want to start with that straight away, but it's very important to separate the reality of what is AI right now and what is currently science fiction and wrong understanding of what AI is. Because there's a lot of people who are not involved in AI necessarily in the industry interested, and they can hear the words AI and they might start thinking that it's robots that are going to take over the world, which, let's be realistic, that's not going to happen, at least not anytime soon. It's important to make the distinction and clarify what is AI, what are the two approaches we see AI. So I'm going to start with the reality where we are currently, what kinds of AI systems and models and methods we're seeing, and that is what we call the weak AI, the narrow artificial intelligence as it is known. And it's exactly what Monty and Wes mentioned, is that model, that method, that it can do a task, a very specific task very well, sometimes even better than a human can do it, but it has limited understanding as to what is it actually doing, essentially? And that is the reality of where we are currently. And then on the other hand, you've got what is considered the strong AI and artificial general intelligence, which is AI that has cognitive abilities and can understand things and can do things without being trained or having experience and so on. We're not there yet. We're decades away from something like that. It's something that is currently science fiction. And what I mean by science fiction, before anyone gets offended, because there are people who are working and doing research on artificial general intelligence, is that it's decades away. It's something that needs unprecedented and unexpected breakthroughs, technological understanding of how the human brain works, the cognitive abilities of a human, if we're ever going to achieve what we call as artificial general intelligence. It's not a staged approach from where we are right now. It's something completely different that we are even having trouble grasping the concept of artificial general intelligence to begin with. So when I say science fiction, everything is science fiction until someone does it, basically. And then it stops being science fiction and it's just science then. And that is a very important thing, that just because I call something science fiction doesn't mean it's never going to happen. It's just something that is quite far away for the time being. And quoting from an older article that I've read from an academic who specializes in robotics, he also makes the comparison that we are as far from general artificial intelligence as we are of flying at the speed of light for commercial space flight. And it's just to show how much way we have to go until we achieve something like that, if we ever achieve something like that.
Okay, absolutely. And so, talk about where we are actually right now, because a lot of people we have in this this webinar are involved in this, actually in the industry, putting out some of these things. And so let's have an honest comment. And I'm going to go to Wes for this. When you really look at what we're doing nowadays, the systems that we're deploying, some of which are actually flying, and congratulations on the FAA and EASA both certifying some of these things lately. How much real AI that people think of is in that, and how much of it is just normal everyday software?
It's a great question, Bill. The perception for someone out in the public when they read about a new system that seems to have intelligence or seems to have the capability of being able to adapt to its current environment and help the pilot make decisions, oftentimes those systems are called AI or machine learning systems, when in reality they're just algorithms that are running in real time on the aircraft, maybe predicting, for example, where the aircraft is going to be 5-10 minutes from where it is now, maybe predicting the most optimal trajectory to a landing, maybe predicting traffic and then helping the pilot avoid that traffic. Those systems are intelligent systems from the standpoint that they have models running and they're helping the pilot make decisions with some simple optimization algorithms, but they're not necessarily AI or machine learning. They are new and novel from the perspective of being able to allow the aircraft to have new capabilities to assist the pilot, almost like a digital co-pilot to help them make better decisions. But ultimately, in those cases, most of the time, we have an expectation where the pilot is still able to take over in the event of a failure of that system if it's a flight critical function. The place where we're just beginning to delve into is systems like the recently certified Garmin Autoland system that basically in the event of emergency can actually look for and identify the best landing site to put the aircraft back on the ground with a single button push. And that is a level of new functionality or taking advantage of existing technology in a new way, really. But the key to certifying that system was to bound where it can be used and how it can be used so that we could gain some experience with its use to show that it can be used safely. And that is sort of this assistive or emergency use idea is the first step or the on-ramp to using this type of technology for more regular use, more critical use in the future. And so for certified systems, we have to introduce things on a risk-based strategy, and that's kind of what we've been doing. We also have companies now that are proposing complex algorithms that have some component of adaptability in them for use in other applications other than the one that I mentioned. And in all those cases, we're looking to bound the behavior of those algorithms to make sure that they can't damage the aircraft and that they, in the end, provide a net safety gain or an improvement in safety over what the aircraft would be without it. And so that's kind of our key to it, introducing these things in a risk-based manner.
And so an awful lot of what you're doing when you're with these new systems is stuff that's covered under the classical DO 178C and normal software safety things, and where you get out of the ordinary, you sort of keep the bound very tight, right?
In some ways, yes, but in other ways, the way that we're sort of leaping out into a new area is we may not have complete understanding of how the logic might be working inside of a particular black box, which is required for DO 178, that traceability of function. But instead, we can put bounds around that black box and say, as long as the input data and the output data are clearly understood, and the function of the box and its impact on the aircraft of the function that it's doing, as long as we can bound that behavior, then we can implement those types of systems safely without having to necessarily understand exactly how everything's working inside that black box. And that's a new paradigm. It's not new from the perspective of aviation. There have been several X-plane programs and several military programs where they have done technology demonstrations with this type of bounded use of these types of adaptive algorithms. But it's new territory for the certified world, and so we're trying to take a methodical and a very a purposeful approach to this implementation so that we can do so safely. Some new functionalities that might give us new capability that wouldn't have been possible without this technology being put into certified aircraft.
All right. Well, thanks for that. And Alex, I think I saw you nodding during all that, so I think you're sort of on the same path.
Absolutely, and I think you're going to see me nodding a lot throughout this discussion, because we do completely agree with the approach that's currently being taken, and we do believe it's the right way forward. Is how do you essentially build trust in a system that you do not fully understand, or you don't have transparency as to what goes on inside that, let's say, black box, essentially. Wes mentioned bounding that problem, that system, to certain constraints, let's call them, so it doesn't go, if something were to happen, it's not going to cause, for example, a chain reaction of events that could lead to a catastrophic failure or otherwise. So it's about being able and ensuring that you can isolate the system, you can test the system, you can make the system even operational to some degree, as long as you're assured that it works as it's intended, essentially, that it does what we expect it to do. It remains within certain safety boundaries, if I can call them that it might not always have the same outcome, but whatever the outcome, it always remains within the desirable bandwidth, essentially. And from there on, it's also what happens in a worst case scenario. So what happens in an unexpected scenario? What happens if we encounter something we didn't plan for, that the system wasn't trained for? Is the system going to take a decision that is going to lead to an unexpected, unwanted behavior, essentially? And how do we manage that then? And starting to look into this system, there's a staged approach as to how do you test it, going from ground testing to airborne testing, for example, if we're talking about airborne systems, obviously. But it's also the level of authority, I guess, that system will have. We can start by having the system and monitoring what would be the outcome in this scenario without actually acting on it in a real world operating environment. And then slowly we can transition to actually allowing that system to act on those decisions as well, given that we've built enough trust that it's going to take the right decision when the time comes.
Great. Okay. Well, thanks. And now let me get over to Monty. And I will confess that, Monty has written some great pieces that I've read, and which did a really good job of explaining that this isn't all going to be that easy. And a lot of the people online probably are familiar with DO 178 and so on, and some of the things we're talking about. But let me hand it over to Monty for a perspective on what the challenges are as you get these adaptive, if you will, or non-linear systems being plugged in. And so maybe you could give us a little bit of that problem statement there, Monty.
Certainly. Thank you, Bill. Well, just moving on from what Alex said, to be honest, I see the problem is the black box. Let's call it that for the moment, and then we probably all know what we're talking about. You know, the black box is where we don't fully understand what's going on, but something has happened, and we may like the result, we may not like the result. I think we should be striving towards a white box. And in other words, what I mean by that, for those not familiar with the term, is that we know everything about what's gone on inside and why it's come to the decisions, why the AI system has made a decision, and we know the input, and then we know the output, and we know what's gone on in between. It's traceability. And that traceability, I think, is key, because with the full traceability, we know when it's gone wrong, we know why it's gone wrong, and we can stop it before it gets to any critical region, particularly in a safety critical environment. Bias is another problem, which Bill, I'm sure you're going to allude to or mention. And in some ways, the two are intertwined, because if you've got bias inadvertently in the data set, in the user input, in the programmer language, if there's bias built in there, but if you have full traceability of the inputs, the decisions, and then the outputs, you therefore can figure out what that bias is and do something to change it or get rid of it before, again, it becomes an issue in this safety critical environment. So I think the two challenges are fundamentally traceability, and to some degree, it's a bit of a side issue, but it does go hand in hand, is bias, and those have to be overcome. I think we can say quite safely that it's very easy to say we need to sort this or deal with it. I think it's a very difficult one to do, particularly when you've got some very mature AI and machine learning systems that don't have traceability. So we're not talking about taking an off-the-shelf program and using it and modifying it for our own purposes in the aviation aerospace industry. We may be talking about a new language that's built from scratch to provide that traceability and the identification of bias and the removal of bias on day one, at the very beginning, when a code is starting to be put together for to support a system.
Well, there you go. Okay, so yeah, it's not all that easy, but it does seem like there might be some rewards at the end of the rainbow if we do get it right, because it does do some things that might be better than humans. I think you'd agree to that, right?
I'd certainly agree with that. It's let's look at a simple analogy. Computers are good at memorizing things. They're good at recovering that data in memory. That's why we have hard drives the size we do. What the human is good is perception. It's awareness, it's context. These are things that the human is good at, making decisions based on what's the weather doing outside, what's the weather doing on the runway, on the ground. We can make instant split-second decisions, and we're good at this, particularly with experience and training. Machines aren't quite so good at this, and they're very much reliant on the data and the quality of the data and the lack of bias within that data to be able to learn and then therefore apply the learning. But they're not good at context. And so, we're good at some things, computers are good at others, and maybe the way forward and for the foreseeable future is to marry those two together, so you have an AI machine learning system that supports the human, takes the workload off, prevents nasty situations arising, and actually warns if they're likely to, but doesn't put us in situations whereby we can't get out of. So we don't give it too much authority and too much autonomy. We tread carefully.
There you go. I think one of the advanced questions we got there was specifically what's our view of the sort of crawl, walk, and run. And yeah, so I think it's a system learning in the background, and then a system being evaluated as to whether it adds value for advisory, and then maybe then a system that does something with an approval, and then maybe someday a system that works by itself. And so there you go. Okay. So it's worth doing, it seems. And I also want to point out to people that I've got two regulators on board here that are not running away screaming at the idea of doing things a little different, and are actually quite forward-leaning into finding a way to make this work. And so I think that's pretty noteworthy, having spent a few decades in the regulatory world myself. I'm kind of proud of that. We may be old, but we're not, with the exception of Alex, we may be old, but we're not stodgy. Okay, so let's go and, well, I have a question I'll just throw out of the blue here. Everyone wants to talk about autonomy, and as they say, that's in the business case of billions of dollars worth of investments. Can we do autonomy without AI and machine learning? I'll leave that open to any of you. What do you think?
I could jump into there, even though I'm feeling like I'm jumping into a pool of sharks right now with that question. But
Yeah,
I'll give it a go. It goes back to the same discussion as to what is really AI, and those kind of discussions never have a firm answer. Basically, not even the experts can agree between them most of the time as to is this AI or this not AI, and we have the same issue as to is a system automated or is it truly autonomous? And there's a huge difference between what is something automated and what is something autonomous, that we seem to lack a common agreement as to where is the line between automated and autonomous systems. A lot of people will argue that, autonomous is a system that employs some form of AI or probabilistic models or something of the sort, and automated systems are essentially just a closed-loop control systems, a feedback control system, essentially. So there's no agreement on that. You'll see different entities coming up with different definitions on the word autonomous and what we mean by autonomous systems and autonomous operations as well. I'm not here to say that you need to have AI to be considered autonomous, but on the other hand, just because something is done without human intervention does not mean it's autonomous as such. It can be just a simple automated function, a simple script, and that's it. That does not make it autonomous, though. The bigger challenge is that you're now talking not just about an autonomous system that could very well have an element of AI, and most likely will have an element of AI, but it's also the question as to how do you integrate that system into the wider, I was going to say ecosystem of aviation, because aviation is a system of systems, and you can't develop anything in isolation. And this is applicable both to autonomous systems, to AI, and all those new types of technology. You can come up with the best idea that works brilliantly. If it cannot integrate with other airspace users, if you don't realize the fact that you're not alone in the airspace you're flying in, and you need to be able to communicate, you need to be able to navigate. If you're only doing all of that in isolation, it works great in isolation, it does not mean it works in the real world. So all of those challenges associated with AI, when you put that AI model into an autonomous system, you're exacerbating all the challenges from there on by having to consider the operating environment as well of that system.
Thank you. All right. Anybody else want to jump in that Shark Tank, or did Alex cover it off for you?
Well, I have some thoughts, but I also wanted to see if Monty wanted to go either way.
I think it's to you, Wes.
Okay, so yeah, I'll jump into this. So this has been a topic that's been near and dear to my heart for a long time, because this idea of autonomy, it's certainly a future goal that we would all love to see in a lot of different aspects of our lives, whether it's in self-driving cars. And if I could sit and read a book while I was going to work, after COVID, where we're all going back into offices or whatever. For aircraft, the interesting thing is that, really all autonomy is a combined system of automated functions that really work together to achieve this high level of automation or autonomy. And so this is why we've taken a functional approach, and why we've been getting away from what we call levels of automation or levels of autonomy. Instead, we're basically just trying to break that down, the functions that the pilot does, the functions that the air traffic controller does, and the things that have to happen to make a commercial flight happen safely. And then to look and see if automation is ready to take over each of those functions. And what we've seen is a lot of very optimistic companies that are new to aviation, and they'll fly a prototype in their back lot, and they'll do some demonstrations on a small, subscale prototype, and they'll show that they can fly A to B or A to A, whatever it might be. And then they say, okay, we're ready to have automated flight. But the interesting piece is they're not really taking into account all the contingencies and as Alex mentioned, the safe integration into the airspace, and how we currently have a very high level of involvement from human pilots in every aspect of the flight. Yes, we have four-dimensional flight path control through modern FMS systems that can fly A to B. We have auto takeoff systems now and auto land systems that are certified. But what's interesting is all of those are built on the assumption that there will be a human that can take over if there's a failure. So the idea of autonomy really hinges upon making systems reliable, safe, available, having a high level of integrity so that they can deal with not only normal operations, but contingency or off nominal conditions. And that's a very tall order. It's not to say that it can't be done, but it just means we're moving things from a technology demonstrator phase to the real world operation. And so the more we can do to have these technology demonstrators, and the more work we can do in partnership with industry to continue to automate functions in a safe manner and show that the systems are capable of taking, not only control, but maybe also in the future perception. Those are things that have to be methodically addressed. And so, we're excited about the possibilities. We're working with several applicants to work towards a high level of automation, but autonomy is still something that's out there a little bit in the ether, because we can't really quantify what the X factor or what the safety factor that a human pilot brings to the operation just quite yet. So it's a tall order, but something that we're all working towards.
Okay, so first of all, you get a situation when your AI just makes that pilot better and better, step by step, crawl, walk, run. Got it. So let's, you were starting to go into this, and I want to make sure that I give everybody a chance to acknowledge how much work is going on around the world in this subject right now. I mean, we have, standards bodies that are on the call right now who are doing some of this. We have seen several documents come out of Europe. We've seen some OPSCONs out of FAA. And so would either of you, with Wes or Alex, start out by just giving a summary of some of the things that should be acknowledged that are going on, some of the work that's happening?
Sure, absolutely. And I mean, we see this becoming more and more of a hot topic in the industry, and more entities coming up with new ways to incorporate AI in the solution. And taking a step back to the previous question as well, is the fact that there's lots of benefits, and we do realize how many benefits there are if we're able to actually incorporate safely such a technology, whether it's in airborne systems or ground-based systems. We can improve safety, we can improve efficiency. There's so many benefits of utilizing the technology, obviously, if it's done in a safe way. We've seen the technology being used in autonomously taxiing, takeoff and landing from one of the big aircraft manufacturers. We've seen air traffic service providers utilize artificial intelligence to reduce the separation distances in airports in London, for example. So we can see the practical applications of AI as well slowly becoming a reality. We might not see tomorrow a widespread adoption of it, but we are seeing the first steps towards those systems becoming the new norm one day. Why not? I'm going to say it. And that is so important, because not only the industry is progressing, but it's also our understanding as a regulator as to what kinds of things are out there, what is the industry working towards as well. And it's one of the things we're very open, and what we want to do is work with industry a lot more going forward, so that the regulator as well is being kept up to speed with all these developments, the plans, the vision the industry has really, and how can we as the regulator help support those efforts in advancing and modernizing the industry going forward.
Okay, and so yeah, there are things that are going to probably have to be adjusted in terms of standards and so on and procedures, but it looks like at least regulators are leaning into it. Anything to add there, Wes?
Yeah, sure. So this is a great question, Bill. And the reason I like it so much is that we've been working for, gosh, I think more than 5 years with industry to try to create crack open the door on this type of adaptive technology and certified systems. And so we started, Steve Cook at Northrop Grumman, myself, and a few others, we started working on a standard with ASTM. It's 3269 is the standard number, and it basically was bounding the behavior of adaptive systems or adaptive functions. And the reason that we started off with that sort of simple architectural standard, it really is just a suggestion for architecture of having a controller or an adaptive function, and then having a recovery controller in case that, you know, black box fails, that you have a system that takes over to get the aircraft safely back on the ground in the event that your, you know, AI or adaptive function fails. So this was basically an architecture that is very similar to what NASA and Mark Skoog at NASA had designed for the auto GCAS system that's flying on the F-16, and has been responsible now for, I think, 11 saves on those aircraft. It's a case where the technology actually can take over control of the aircraft without the pilot having an ability to override it. And it's a new paradigm, basically, because normally our certified systems, the pilot is the primary, you know, responsible entity. Well, in this case, if there's a pending accident, like a loss of control accident, or, you know, a G-induced loss of consciousness, and the aircraft is going to hit the ground, this ground collision avoidance system takes over, flies the aircraft to a safe, you know, altitude, levels the wings, and waits for the pilot to wake back up. What's interesting about this architecture is, you know, as it allows for a particular function to be done to save the aircraft in the event that the pilot's not doing the right thing. And so that concept of on a very functional, you know, very specific basis, allowing systems to take over, no longer just assisting the pilot, but being responsible for safety, that's a new paradigm. And so we wrote that ASTM standard as a starting point. It's been revised a couple of times now with a broad group of members from industry. And so we're really happy that at least is starting to crack open the door on this idea of very specific functions being implemented to assist the pilot. And Monty had mentioned this earlier on. You know, we need these instances where we have a clear understanding of how the function works, and we can have that traceability, the white box mentality of exactly how that algorithm works, and allow it to take over, and, you know, be able to do this type of complete traceability of function. In that case, you know, this does have a very traceable you know, way to look at how it reacts and how it interacts with the world. But it was a new paradigm for us to allow a system to take over and to override the pilot. And so that's kind of a starting point. And, you know, I mentioned the Garmin Autoland system already. We're working on several other technologies like that with some of our applicants, where they're using technology moving from an assistive manner into a safety critical, responsible manner. And so this is kind of the new territory for us.
And so I just was looking, I had a question pop up while you were talking about, let's see, with just a second, I lost my scroll, but basically we were talking about, so when can, so let's say a pilot does something wrong, and then the automation is able to intervene and prevent it. Well, that's to some level of the ultimate guardrails, you know, are the limits in an Airbus, right? That's not a real new thing. But basically, where are we at in getting this idea of automation able to save an aircraft? You've already mentioned the Garmin Autoland, and there are others in the works, right?
Yeah, so I think, you know, the way that we have viewed this implementation of technology is, and the way the EVA architecture that NASA invented, Mark Skoog I mentioned earlier, it's just a variable architecture for automation that can be adapted for multiple functions. But the idea is to protect the aircraft from hazards that are easily identifiable, like a pending, you know, controlled flight into terrain, or if an aircraft was about to fly into a thunderstorm, if you had good information on where the core of a thunderstorm was in a timely manner with some type of margin around it for you know, time and things like that, you could have aircraft avoid those storms automatically avoid other aircraft automatically. And it's sort of the analogy of the bowling alley where you put up the little guardrail lanes, and when the kid's throwing the bowling ball down, the ball can't go out into the gutter. These things are just better implementation of envelope protection, but not at the aircraft state level, like angle of attack limiters and things like that, but more at the trajectory management level, where we're managing the four-dimensional trajectory in a safe way, which is really what the intent of the pilot is all along. They're managing that flight path and that trajectory to get from A to B safely. So these types of algorithms, these types of implementations should be meant, first to make them better at that job, and to maybe automatically avoid hazards, so the pilot, if they're not taking the right action, the system can help and save the day.
That's
all right. Yeah, go ahead.
Just to jump in there, that's a very interesting point, and it's also worth presenting how many challenges we're facing there, even the more philosophical challenges rather than technical challenges as well. But the idea of having an AI-based system, or any kind of system that can take the correct decision if it's seeing that the pilot is not reacting correctly, maybe the pilot is incapacitated, is great. And hopefully one day we can get to that point where we have a safety system that if something goes wrong in the cockpit or otherwise, it can actually take control and land safely the aircraft. That would be ideal. The question that one of the big challenges in this scenario is, how do you ensure that in a normal operation, there's not going to be some form of error or a sensor reading or something that basically triggers that system, even though everything is working as it should, but the system, through to various reasons really, could basically activate itself and cause any kind of incident or accident down the line as well? Because going back to what Monty mentioned in the beginning, AI is still lacking that human judgment to understand whether a sensor reading is realistic, is wrong, or if you can tell by that, that sensor is probably not right, and you can take that decision. And there are ways to start mitigating against that, absolutely. I'm just showing that even implementing something like this, the risk is, how do we avoid it, basically any unexpected behaviors outside its operating conditions?
Okay, well, there you go. And as I'm transitioning into some of the Q&A here, I have a question here. This is when you talk about these black box systems with bundled, and these things always move as soon as you start reading them. All right, with black box systems with bounded behaviors. So what's the architecture of all this? And I think Wes just mentioned architecture a minute ago. Are you going to have a bunch of black boxes each making independent decisions, talking to one another, or do you have some sort of architecture above that to mitigate all these little functions at different level of maturity that we're going to be implementing?
Yeah, so this is a really exciting area that we're working with NASA on right now, and that is this idea of multiple. First of all, we're talking control and not perception necessarily of certain functions. There is some limited amount of perception if you call, a sensor sensing, weather, or a sensor that's, looking for other aircraft, or sensing, the proximity to the ground, and then putting those inputs into the control system. Those are, sort of perception in a very limited manner, but mainly control functions. And what we have in the architecture that NASA has designed is it has what we call a moral compass, and it basically is a list of primary drivers that are, the decision-making algorithms or adaptive algorithms are using to make the decisions for the aircraft. So, and they can be dependent upon the type of aircraft and the use case type of mission the aircraft is flying. So an example would be, you could have an algorithm that's protecting an altitude limit for a small unmanned aircraft, that it won't go above a certain altitude, so it's staying out of other traffic. You could also have, at the same time, an algorithm that's looking at, you're looking for other aircraft, maybe near airports, they want to make sure they're still avoiding, low-flying aircraft. And then you could still have yet another layer on that where they're in a particular geofenced area. They're trying, basically bound to flying in an area. The difficulty, of course, is prioritizing those different protection schemes and those different control loops to say, okay, well, who has precedent? Can I break like a geofence boundary if I'm avoiding another aircraft, or can I break an altitude limit if I'm avoiding the other aircraft? So in that case, that the collision avoidance algorithm would have precedent, but they all would be working at the same time, and through the architecture that NASA has designed, the system is capable of taking all those inputs and deciding what the right trajectory for the aircraft is based on those inputs and on that hierarchy of function. And so, it's very basically just multiple runtime assurance and monitoring loops, and multiple, bounded behavior algorithms that are working at the same time to bound the behavior of the aircraft.
And I have to say that probably gets into some of the questions I'm getting, which are right to the core of things. Is so how do the regulators eventually certify these? How do they get transparency? What you've got transparency are in the guardrails, the boundaries, if you will. I think we would call that glue code in the old days with DO 178, right? Because we've been running COTS that we never understood was in it for years, but you have traceability to the software that bounds what comes out of that COTS box, right? So I think I'm saying that right. I better watch it, though. I'm getting way out of my depth there. All right. Hey, let me move into some other sections that we really haven't hit hard, and we'll start trying to jump over to questions as well. We haven't talked much about data and bias and learning. And I think that's maybe a big sea change that a lot of conventional aerospace people maybe aren't completely prepared for. What the hell does a data scientist do? Things like that. What's going to happen when your data changes and you change sensors and so on. So could we transition to that? And Monty, I think you were probably the first one to bring up bias. Do you want to start talking about what this could look like in an aviation context and the things we might want to worry about when we start talking about data?
It's certainly, Bill. Data is a big issue. One of the well-known uses of data is in facial recognition, which I'm sure everyone's heard about. And we might have a data set comprising of millions of sets of faces, many of them the same person taken from different angles. And the idea is that the facial recognition software, of which is relatively mature, and there's a lot of it out there available for open source use, looks at uses the data set. It's trained and learned on that data set, and it can then recognize who that person is from the knowledge that they were in the data set and it was trained on that data set. That's a simple example. If we then take that and apply that to aviation, we can instantly see that we're operating in a 3D environment. It's not just two-dimensional, such as cars, roads, traffic, buses, railway lines. Three-dimensional is varying weather conditions, which will affect the aircraft, height, altitude, terrain, different airfield configurations. It's a big area, and we've got to actually start off slowly, cautiously, and move ahead at a pace that is well within the capability of the AI and the AI systems and the demands of what we're trying to put on it, so that we retain safety, which clearly has to be paramount. So the data can be absolutely enormous. If you imagine the data sets that would have to be used for even a routine transatlantic flight, with the possibilities of variations in weather, of airfields at each end, runway conditions, lighting conditions, runway lights, it is enormous. And to train a system on that data would take a long time, and to test it and ensure that it's rigorously applied such that it is safe, again, will take a long time to work through the system. So I think there's a big challenge there, and the way to start off is slowly, bit by bit. Don't ask too much of it. Let's look at data in discrete parts of the system, such as one of the boxes in the aircraft. Let's look at autonomizing that part of the aircraft system and using the data that's only related to that. I think there's where I start becoming quite concerned is where we're asking the AI via machine learning or just via pure programming languages, we're expecting it to undertake functions where the human would normally routinely undertake, and where that human relies on context, perception, general knowledge, all the things humans are good at. And we mustn't stray into that area, at least not for for considerable time in the future. We have to apply the bit by bit, the building brick approach, and be fully confident that what we're asking will be absolutely 100% watertight and will work and will not let us down. I think it was Alex, you mentioned earlier about one of the how that controlled flight into terrain, and I see it's come up as one of the questions on the chat. Yes, AI can help prevent controlled flight into terrain. It can be done. It can be applied, but it's got to be done in a manner that allows for the fact that a sensor may be out. And whereas the human can look at 2 or 3 sensors in the aircraft and look out the window and realize, actually, we're okay, or no, we're not okay, the AI has to be able to take all that and apply the context to ensure that it's not going to take over or provide a massive input in the wrong sense or the unsafe sense. Likewise, there's an old saying, don't turn a minor calamity or a drama into a major emergency. If it's safe to land, carry on landing. A go-round initiated because the AI decides that it doesn't like something when it's completely unnecessary to go around, that go-around could cost fuel, could set up a diversion, which actually becomes a major emergency in its own right. So we've got to ensure that what we're doing is safe all the way along. And I know I'm harping on about it, but I think it's the fallback position that everyone has to recognise and think of. Is this safe? Is it sensible? Is it watertight? So my message there is slowly, bit by bit, and let's not bite off more than we can chew. Let's apply this to small parts of the aircraft system until we've got the confidence and the capability for it to then move ahead into more difficult areas.
All right. Well, thank you for that. And again, we keep coming back to this, take a bite at a time at this thing. But let me help people that maybe haven't considered this, the problem of how much data you're going to have even to do something fairly simple. Let's say you're trying to get a machine that recognizes a vertiport and plots an approach path to it that's very efficient use of batteries, something you're going to want to do a lot of, I think. So you're going to have data, fly thousands of approaches with a stable set of sensors. You have to worry about bias. You want to make sure it's not actually teaching itself just to land 253 meters from the red food truck, right? That it's actually seeing the things it's supposed to see. And for developers, we'll have to train the system, and then people are going to have to test the system, and then regulators are going to have to validate it. And so how are we going to manage all of that data? What does that look like? And I'll try to put either Alex or Wes on the point for that. So you need separate data sets. How many data sets? How big are these things going to be, really?
Well, the answer to how much data is huge, regardless of what you're trying to do, I guess. I mean, even if it's a simple operation, if it's a very complicated operation, it's always going to be huge amounts of data. But it's also important to note that it's not just the amount of data that you're using to train the model. You need to ensure that those data are obviously clean, as we call them, so they're complete data and so on. We need to ensure that they are representative as well of the eventual environment that system is going to be operating in as well. If you train one thing to do one very specific task and then you put it into a completely different environment, then you're probably setting it up to fail. So you need to ensure that the data you're using to train that model, you have enough of them, you have representative data of what eventually that system is going to be employed within a specific environment, essentially. But now you also posed another question about how do you trace any possible changes down the line as well, because let's be honest here, AI is not going to be a model that you train once and then you put it onto an aircraft or any kind of airborne system and then that's it. It's going to take some form of maintenance or some form of retraining down the line. So as those systems are getting more and more, let's say, flight hours and operational hours, they start gathering data. And one of the most important things that need to happen when those systems start flying is monitoring how those systems are behaving, essentially. So you can gather more data, and then the next time you come to train a model to do that thing, you have a better understanding of what worked last time, what didn't work well last time, as much as you can in terms of understanding, because you've you've touched before on explainability on AI, and it's a huge topic that you might not understand why the system took a certain decision, or why did it turn right instead of left, for example, if it was as simplistic as that. And we need to understand, to a certain degree, the sensitivity of a trained model to those training data. And what do I mean by that? Let's say we've got a data set and we use that data set to train a model. Let's call that model 1. Let's change those initial data, or let's add data and retrain a brand new model. Let's use the exact same parameters we used to train the previous one, just use different data. So now you have 2 different models that were built in exactly the same way, just using slightly different, let's say, training data. You can put those 2 models into the same kinds of scenarios and see how they respond. So you can start getting some understanding as to the sensitivity in those initial data that you used to train to the eventual output or those decisions that that system is going to take. This sort of sensitivity analysis can happen along the entire life cycle of a system, from building the system, designing it, and so on. I'm just giving a very simple example why those data are so important, especially about systems that we expect them to be retrained down the line, to be taken offline, improve them in some way, and then put them back in the air. I expect the question to come, do we need to recertify those things? I don't know. I don't know how the approach will be. And it's a huge question we're having ourselves there. But it comes to show that data is undoubtedly the cornerstone of any kind of AI developed model.
Yeah, and I think that's something you can't underline enough. And in my own view, if I can interject as an old program manager, this is probably one of the larger risk areas, because we're used to configuration managing code. We're not used to configuration managing data and metadata. And that's something I think the regulatory system is going to have to grow into for a bit. And also, if we have a bunch of different people training different little functions, how many hundreds of databases and test databases are we going to have all trying to describe what a vertiport looks like? It could be quite messy. But that's my own ranting. Wes, you probably have more informed opinions than me on data and bias. Anything to add there?
Well, I think, this question of data is obviously one that is very dependent upon the system and the function that the system is performing. And hidden behind the data question is the question of the model itself and the physics of the model. So what's interesting is that if you go to a complete AI black box approach where you just feed it data, you let the model develop, and you prove that a certain large set of input data gives you an acceptable set of output data without really caring so much about the physics of the model internally, that's one approach. And that one really requires massive amounts of data, because as it has been mentioned, Monty said, you can basically have some bias in the system, or this idea of overfitting the data, where the model becomes only capable of regurgitating the input, the training set of data, but as soon as you give it something from the real world, then it can't match it or can't repeat it. The key behind that is the function and the physics behind the function in the model. So what I'm driving at is a lot of the new tools that are being used for the use and application of AI are simply data regurgitation or data management tools. They may not have the understanding of the physics of the problem behind it, and that can be a double-edged sword. An example, we have our local university here, University of Kansas, is doing some research for the FAA, and they have designed basically an AI controller that was able to control a drone, a small UAS, basically for test purposes, and it identified a control model and was able to handle disturbances from gusts from the atmosphere and things like that, and handle the flight path for the aircraft very quickly. And it was a completely different model internally than the typical equations of motion that have been used on some of the other controllers for these types of aircraft. In one hand, that's really exciting, But on the other hand, you have to, to Monty's point earlier, if you don't have the white box mentality of understanding what's going on, it's very hard to trace when a failure occurs or when the system decides to do something that doesn't make sense in the real world. So we have this this balance, basically, of being bound by a physics model that matches our typical understanding of how aircraft fly, and being bounded by that versus allowing it to be completely a free space and allow these new controls and perception algorithms to create a whole new paradigm. And it's kind of a double-edged sword as to which way you go, because for the understood physics models, it's easier to get that traceability through the system of what's happening. If you let it do something completely new and novel, then it becomes harder to understand. And that's where these training data sets come into play. A clearly understood physics model that's being tweaked a small amount by AI is one story. The other end of the story is having a completely new model that is very dependent upon having a huge, training data set to get the right outputs. And so that's a decision that each person, each company implementing AI into their aviation application, they'll have to make a decision on that, because as Alex mentioned, once you get into, the certification of these systems that are very difficult to understand, or the training and input and output is not clearly understood, that can become a certification challenge in itself.
Yeah, and I'd like to add that it's not just a certification challenge for a regulator, but if you're an OEM, you're probably subbing a lot of this stuff out. And yeah, you have the same problem, only it's an economic one to determine whether or not you're being delivered a system that's just been trained to do, basically turn the algorithm upside down, and it just does what it's the algorithm told it to expect. And so, yeah, and it's a question of, I think, do regulators have to get smart in data, maintain data sets for test? How does that done? Do OEMs have to do the same thing? And so, and you also, I think, hit something really, really important, which is this idea of the physics model, which I'll translate into saying domain expertise plays a role in this. And so finding a data scientist that understands AI and has domain expertise is probably going to be kind of important. And then the regulator's going to have to find someone to verify they got it right. How are the regulators standing up? Are we developing that type of data scientist insight? Or is it where we're going to have to go next to get this right? I'll leave that up to either Alex, Wes, Monty, whoever wants to jump in.
I can start with that, and that is one of the most crucial things that a regulator needs to do essentially going forward when it comes to this kind of, and it's not just about AI, it's about any kind of new technology that is coming our way, is that you need to ensure that you have the relevant skills in-house to be able to oversee and ensure the safety of these kinds of technologies. Because let's be honest, if you don't understand something, how are you expected to regulate it going forward? How can you take a decision if something is safe, and how can you answer the question, what is safe enough when it comes to these types of new technologies? So training, education, new skills, it's a very important thing for a regulator to be kept up to speed with what's going on in the industry. Something that, at least for the CAA, we are looking into as to how can we educate the regulators as well, bring new experts in, bring new specialists in that can advise and basically educate the teams that will oversee these kinds of technologies down the line. Because again, you do need to have some level of understanding, a certain level of understanding at least, if you are to understand the implications of these new technologies going forward.
You're right. Okay. Anybody else want to jump in on that mess?
Yeah,
that's a tough one. All right, Wes, you in there? All right.
Well, go ahead, Monty. That's all right.
Oh, okay.
All right.
Thanks, Wes. I'll keep it short. I'd like to just make the point that one of the critical aspects is that when you're developing the AI, the software, it's going to involve a lot more closer cooperation and involvement between the regulator, the software engineer, the data scientists, the guy in the cockpit, and anyone else who actually has got an input into that system. Maybe the third party who's giving you the black box, which you'll want to have some autonomy over. they're going to have to work closer together than currently happens. It's not just a case of passing it online, subbing it out, and it comes and it works, and you plug it in. This is a whole new ballgame, and it's something that will have to be built into the architecture of how the software in the aircraft as a whole is built, enabled, and then put into service and tested to be completely safe. I think it's a different way of working, and it's one that the industry will have to get its head around.
Absolutely. I think you've got that exactly right. Nothing scares me as much as the concepts of subbing out and stovepipe development in this context. Wes?
Yeah, just really quickly, we've seen the evolution over time in certification of safe systems on aircraft. If you look back, in the early days of aviation electronics, which we call avionics now, we needed the systems engineers, the electrical engineers, the human factors people, the pilot, that team came together to certify safe systems. When we started having software-driven systems, we added the software guy to the team. And now that we have AI and machine learning coming into these types of systems, we need those data management and, adaptive system experts to be part of that same team. It's not that we've let anybody else go from the team. We still have the human factors aspects. We have, but now it's human machine teaming aspects. You have, the pilot is still an important part, as Monty mentioned. I think one of the things that the FAA has been doing is not only to try to make sure we are having internal expertise in these areas to a sufficient level to understand what our applicants are bringing to us, but we're also really leveraging more and more the use of industry standard bodies. And part of the philosophy behind that is we can't move at the pace that we're being asked to move for embracing new technology on our own. And we could, but we really benefit greatly when we have partnerships between us and the industry standards bodies to move to bring new technology safely into the aviation environment. And then we've also begun partnerships with NASA and with the Department of Defense under our Agility Prime, under their Agility Prime program. All of those things are meant to bring to bear the complete skill set of all of those different entities so that we can solve these kinds of problems together. We have learned from experience in the FAA, if we try to do it on our own, we oftentimes are behind the pace of industry, and we don't want to be the driving force that's holding things up. We also don't want to let things, go completely unfettered, because we want the same things to be introduced safely. And I think those partnerships are key to that, from moving technologies from prototype to, use in a real safe civil operation.
Well, I have to commend you. You always know you're getting to the core of things when you stop talking algorithms and start talking organizations and people and functions, because that's where it actually, almost all the risk tends to be, in my experience. We're getting towards the end of the session, and we still have a nice amount of people hanging with us. Thank you. I've been trying to cover off a lot of the questions, by steering the conversation that way. I hope I've done a suitable job. Let me do this. Let me just go back to my panelists and see if there's a few things you want to summarize or forgot to say, or things you meant to say but didn't. So we can, let me go back around to Alex, who hadn't spoken in a while. I'll let Wes recover.
Absolutely. Obviously, we're never going to answer or come up with new standards in a 1.5 hour discussion. I don't think that was the intention, but hopefully we managed to scratch a bit of the surface, at least, as to this space that is called AI, especially the challenges surrounding AI in aviation as well. We know there's a lot of benefits in it, absolutely. We know that anything you automate, you can minimize the possibility of a human error down the line, but let's not forget that it's humans that develop those models to begin with, so you have other challenges there that you need to address as to who designs the software, what kind of data you're using, and so on. We never have time to list all the challenges, from human factors, from cybersecurity, all those things. It's a topic that touches on almost every single functional area of aviation in terms of safety, and that is one of the reasons why this is so challenging. And if I can move on and say what we're trying to do as CAA as well when it comes, because I see the questions coming up about what are we doing, what can we do more, and so on. Can we do more? Absolutely, and we are planning on doing more. I can guarantee you that. The CAA has set up last April in 2019, the Innovation Hub, which is the team I'm currently working in, with the aim to address these kinds of new technologies, whether it's AI, whether it's autonomous systems, whether it's eVTOL aircraft for urban air mobility and future mobility, all these interesting technologies and operations that are coming our way. We want the industry to stop looking at the regulator as the blocker to these innovations becoming a reality. We need to stop seeing the regulator as the entity that is inhibiting and prohibiting innovation to happen. And that's why we've set up this team. We're here because we want to work with the industry. It's what Wes and Monty mentioned. If those things are going to become a reality, all of us need to work together. And this is something I'm particularly very happy to be working in this industry, because I'm seeing how many competitors are now working together to overcome different challenges that we're seeing, how closely now industry is working with the regulator through working groups, through initiatives of the regulators as well. And this is the way forward, I believe. It's standardization agencies, academia, industry, regulators, everyone collaborating. If we are going to come to an agreement as to what is a safety solution, let's say, to making these technologies happen. We are launching programs in the Innovation Hub where we actively ask entities to come and talk to us. We can sit behind closed doors in working groups with other regulators and come up with new policies. If we don't know what's going on out there, those policies are not going to be realistic. So that's what we want to do. We want to talk to the industry, see what's being developed, see the direction that the industry is taking, see what is the demand from the regulator, and work with the industry to come up to an agreed solution, basically, as to how can we make things happen, and the regulator be seen as supporting innovation and not prohibiting it.
Okay, thanks. How about we go over to Monty for your last thoughts?
Thank you, Bill. I'd like to just go off piece slightly, if I may. There's a good story to be told about how the banking sector has moved forward in software terms over the years. And many of you may be aware that the banking software is largely, not completely, but largely dominated by what was COBOL software. That's a programming language from the 50s that has largely gone out of fashion, but nevertheless still exists as the architecture and backbone of many current in-use banking systems on the high street and in the financial centres. Because of the lack of traceability within that software, and because of the lack of expertise in the programming language now, it makes it impossible, if not absolutely impossible, to modify to any degree that software. Hence why you see banks suddenly go offline for 2 or 3 days because they've tried to do an upgrade. If you're a new bank, new on the street, you're a challenger bank, you start from scratch in 2020, you don't have that problem. You haven't got Cobalt. You'll be writing the language and your financial language in a new programming language. It is fit for purpose. It'll have better traceability, and it'll have the expertise, which in turn leads to better traceability. So I think I'm under no illusion, and my message would be that these AI systems we're talking about, we have to be looking at putting them on future systems and not just trying to nail them onto an old system, because nailing them onto an old is going to invoke a lack of traceability and just create an accident waiting to happen. It's got to be done on something brand new from scratch that's designed to have AI in it and not just tagged on as an afterthought. That's my passing thought, Bill.
Thank you so much for that. And so I'll give over to Wes for your last words on this.
Okay, thanks so much, Bill. Yeah, it's an interesting question, that Monty just brought up. We have hopes that we can actually use some of these new ideas and technologies and adaptive algorithms or decision-making algorithms to improve the retrofit fleet, to specifically for my passion to improve general aviation safety, for loss of control accidents, for controlled flight into the ground, for automatically avoiding other aircraft as we get more and more airspace density as we have, package delivery drones flying over populated areas. We certainly don't want to see an increase in accidents related to mid-airs and those kinds of things. And I think some of the technologies we're talking about today are key to not only, future systems, as Monty mentioned, but also have some, retrofit capability to improve the teaming between the human pilot and the machine for safe operations and for new types of operations. Having said that, my passion in the FAA is to introduce these things in a risk-based manner, to be methodical with industry and partnerships to look at particular functions that are ripe for this level of automation now because of current technology versus fully autonomous, systems that might have to wait on some core technologies to be developed. So, my first point is, we're all moving forward on this as much as we can within the FAA to apply this technology to improve safety. And we're doing it, in a risk-based and task-based manner specifically, so that we can try to reduce some root causes for human causes of accidents. We also are, very hopeful about how this technology will grow in the future to allow reduction in crew workload for future aircraft. We saw for example, we got rid of the navigator, we got rid of the flight engineer, we got rid of the radio operator in the cockpit. A lot of the two crew transport category aircraft now are highly complex aircraft, but the workload is capable for two people because of automation. And I think we'll continue to see that trend moving toward, in the future, potentially aircraft that are piloted with a shared resource between the aircraft and a pilot on the ground. And, moving towards those types of systems for remotely piloted aircraft before we go full autonomous are some of these stepping stones. So, I'll just close with the idea that we have to have a clear idea of intended function and a clear idea of how that intended function is improving safety for these systems to work their way into certifiable systems in the future. And we're ready to move forward with the industry as long as we can do so safely.
All right. Well, thank you for that last summary. I think you've heard a lot of people on the same page here. I'll just remind you of a few things that your regulators are actually out there leaning into this thing, trying to find a way to get it done. That there's things you can do within existing standards to treat things as white boxes, black boxes. And so all is not lost, but there's plenty of challenges left. If we take it bite by bite, function by function, add value as we go, and then we take on the bigger issues of how we organize ourselves around which is always a magnificent challenge. So with that, I'll thank you all for hanging with us for all this time, and I hope you got some good insights and enjoyed the frank and informal conversation, if you will. Look forward to seeing you next time. Good day.